This tutorial will show the power of the ETABS Open Application Programming Interface, or OAPI. We will program ETABS to build this complex-shaped building model, run the analysis, and extract results, all from an external application. In this case, we will use Excel and its Visual Basic for Applications language, or VBA. Although almost any programming language, such as C++, can be used to access the ETABS OAPI functions. Our model for this tutorial will be a 6-story building that is elliptical in plan and whose dimensions vary exponentially in elevation. The building consists of perimeter concrete columns, perimeter concrete beams, a concrete wall elevator core, and concrete floor slabs. For the analysis, the building will be subjected to self-weight only. We wish to extract out the vertical reaction force at the base of this one column and save it in the worksheet. Included with ETABS is help documentation that describes all of the OAPI functions. The document includes general overviews, examples, and the ETABS namespace, which lists the OAPI functions. One function we will use extensively in this model is the add by coordinate method for the frame object. For each function, detailed information on the syntax and the parameters is provided, along with sample coding. We will control ETABS from Excel using VBA. We will also define the geometry for the model using Excel. We start with a spreadsheet that has the X and Y coordinates of the column locations at the base of the building. If we go to the Insert Chart command, and plot these coordinates, we can see that the layout of the columns is elliptical. The building is 100 feet by 80 feet. The spreadsheet also contains a cell showing the number of stories, which is 6. The reaction at the base of the selected column will be written into the spreadsheet at this location once the model is analyzed. We will now start our OAPI programming using the Visual Basic editor provided with Excel. All of our coding will be contained in a single module. We will call this module ETABS OAPI. Before we can start coding, though, we need to reference ETABS so that the application and its OAPI functions will be accessible to VBA. We will need to reference the TLB file for ETABS. Make sure that you read and understand items 2 and 3 as well to ensure that your coding will run. The ETABS TLB file is located in the same directory with the program executable. Now we can start adding our code. First, we add in all of the code that occurs prior to our first procedure, or code that has a module level scope. Here we declare our ETABS variable as an object type using the application and class type, as well as getting a reference to CSAP model. We also declare any variables that will be used across multiple procedures. Next, we add in the code for our first sub-procedure called ETABS open. This procedure opens the ETABS program using OAPI functions. Here we create an instance of the ETABS object, start the application, initialize a new model, read in the number of stories from our spreadsheet, and create a grid using the file newGridOnly function. Lastly, in the subroutine, we save the model. Our second procedure is called ETABS build, which will build the model. We start by creating a coordinates object for our input geometry. The rows count command is an Excel command that returns the number of XY coordinate pairs. We then generate X coordinate and Y coordinate arrays based on the values in the spreadsheet. Next, we generate the building columns. This consists of a loop that generates columns at each story level using the frame object add by coordinate function. However, these columns are not vertical, but have a slope that is produced by exponentially adjusting the endpoints. Following the columns, we have a loop that adds perimeter beams at each level, again using the frame object add by coordinate function. Next, we add in the elevator core walls. These are not sloped and consist of 4 wall segments. These walls are created using the area object add by coordinate function. The last item in our build process is to add in the floor slabs. As we go up the building, the floor plates shrink to match the slope of the columns. Again, the area object add by coordinate function is used. The third procedure we will define will be for running ETABS. We are not doing a dynamic analysis at this time, so we will shut off the modal load case, and then we'll run the analysis. Once the analysis has been run, we select the load case for which we want output, which for this example is the dead case. With the load case selected, we extract the joint reactions for our selected column using the results joint react function. The last step in this procedure is to write the vertical reaction for the joint back into the Excel worksheet. The only reaction we are concerned with is the vertical, or F3. The last procedure closes ETABS. This is done using the application exit function. We will not resave the file. The last step is to set the objects equal to nothing. This is important to break the connection between your application, in our case Excel, and ETABS. Scrolling up, we see that we have a total of 4 procedures. all contained within our module ETABS OAPI. We are now ready to return to the worksheet. With our VBA code complete, we have added buttons to our worksheet to trigger our procedures. The first button starts ETABS, that is, triggers the ETABS open sub-procedure. A right-click on the button shows that the open subroutine has been assigned to this button. The second button is used to build the model or trigger the ETABS build sub. The third button runs the analysis, and the last button closes ETABS. We have 4 buttons, one for each of our 4 procedures. We can now start ETABS from the Excel program. With ETABS now running and the file named and saved, we will switch our left view to a 3D view. Returning to Excel, we now click the Build Model button. First, the column objects are created around the perimeter, and then the beams are added, followed by the core walls, and finally the floor slabs are added. We are now ready to run the analysis. Before we do, note that the cell located under the reaction heading is blank. This cell will be populated after the analysis. Clicking the Analysis button and then returning to Excel shows that the vertical reaction for our selected column is now displayed on the worksheet. The value shown is 164. If we go to the Display, Force Diagrams, Support Reactions command, and select the FZ component, when we zoom in on the selected column, we see that this value matches the one shown in the worksheet. One can see how this is a very powerful tool for doing parameter studies. Even though ETABS was activated from an external application using the OAPI functions, all of ETABS menu commands are still available. And here we ask for F11 force contours to be displayed for the shell elements. With the analysis complete and the desired results extracted back into Excel, the last step is to close the ETABS program. Obviously, one of the powerful benefits of using the OAPI is that various parameters can easily be altered. In this case, let's assume that the owner has decided that rather than a 6-story building, they want a building that is 14 stories. With the way that our coding was developed, simply changing the stories variable to 14 allows us to quickly and easily generate a new 14-story model. In summary, ETABS OAPI functions provide a convenient way to link ETABS' powerful modeling, analysis, and design capabilities to other applications. Although this example used Excel and its VBA language, most major programming languages can be used to access these OAPI commands. This concludes this tutorial on programming ETABS.